Hi guys, it's Miss Bailey here again, this time to talk to you about relative motion. Now, relative motion is just this idea that sometimes movements or motion can look different based on where you're looking at it from. So my favorite example of this is the walking sidewalks or the moving sidewalks, the walking platforms you have at the airport. So here's a guy standing on one of these moving sidewalk thingies. Let's say it is moving forward at some speed. So this whole thing is moving this way. If this person is standing still, to you, somebody who's not on this moving sidewalk, you would appear to see this person moving with the treadmill. Is this person actually moving? Well, relative to themselves, no, they are not. They are just standing there. But relative to you, or compared to you, who is standing on ground that is not moving, they would appear to be moving. This could change based on a lot of things. So, like, let's say he's moving backwards at the exact same speed that the treadmill is moving forwards. You would see this person, and I'll draw some eyeballs. You would see this person not moving, staying in the same location compared to where you are standing. But this person is actually walking this way. But because the motion kind of balances the motion of the treadmill, they, to you, seem to be staying in the same location. If you were on the treadmill with this person, you would see them moving backwards in the opposite direction, away from you. Cool, that's all relative motion is, just how movement can look different from different perspectives. This is another great example of this. So you maybe learned from horizontal projectiles that when a plane drops a package, it makes this nice little half a parabola shape. But you maybe also learned that all objects, all projectiles have the same horizontal speed throughout their whole motion. Velocity x does not change. Because of this, when somebody drops a package out of an airplane, to them, it looks like the package is just getting further and further away. It looks like it's just dropping straight down. And that is because they are moving together with the same horizontal speed. The only difference between the motions of the package and the plane is the fact that the package is falling in addition to moving sideways. So because of this, somebody in the plane would see the package as dropping straight down because that's the only difference between the two motions. Awesome. We have a little bit of math to go with relative motion. Another example of how motion can look different from different locations is a river. Rivers generally have currents that can push something forward or backward, north, south, up, down. I guess not up, down, but you get the idea. So let's say in this first example right here, we have a boat that's moving upstream. The current is pushing, I guess let's actually say north, south, east, west. Just to make this simple. So let's say this river current is going 3 meters per second east. The boat is going 5 meters per second west. What would the person who is not on the river see the boat doing? Well, a lot of you could common sense this and know that if you're going upstream, you would be going slower. But how I really solve this problem is something as simple as vector addition. I'm just going to redraw my vectors over here to scale. 5 meters per second west, 3 meters per second east would combine to make 2 meters per second east. So now this next picture. Now the boat is moving with the current, so it would make sense that their motions build. And in fact, if I move this vector to the head of this vector, I can see that I just add those two motions together and I get 8 meters per second to the east. Now these last two examples are a little tricky. Now the boat is moving across the river. but the river is still pushing it sideways. So what we would see the boat do, we can figure out by redrawing this vector diagram to where those vectors are head to tail compared to one another. This boat would be moving diagonally. It's going across at the same time the river is pushing it down. So to somebody who's not in the river and not experiencing the river's motion, they would just see this boat moving diagonally. And how I would find that side. Be careful here. This is not a 3, 4, 5 triangle because the 5 is not on the hypotenuse. So the real hypotenuse would be about 5.8 meters per second. And I can just say that's northeast. Now the same thing would be true if the boat were coming the opposite direction. I would just have to redraw my vector diagram a little differently. So if you want, you can still keep the 3 meters per second up here as long as the two that you're adding together are head to tail. The new one goes from start to finish. So that boat is still going to be moving diagonally, but at a different angle. The magnitude of this side will still be the same, except now you are going southeast. Remember, south plus east should give me southeast. There are lots of other videos that your teacher may link to a note page that you could watch to get the idea of relative motion. You could also, if you really, really wanted to, on YouTube, the first, I don't even think 5 minutes of the relative motion demo shows a car full of guys dropping a water balloon out of a moving car just driving sideways. And they film this water balloon from 2 different perspectives at the same time. They film it from outside of the car, and then they film it from above, but from the moving car. And you can see how those motions look different. It's kind of an interesting video, and I'm sure we'll watch it in class. Let your teacher know if you have any questions. Relative motion is basically vector addition. So make sure you don't forget your rules from the beginning of the unit.